Hello, and welcome to the video lecture for topic 5, bond angles and distances. So this video lecture is going to be primarily concerned with bond angles. I feel that your reading in Sorrel along with the worksheet activity associated with this topic sufficiently covers bond distances and the information that I feel is necessary for you to have there. So I'm not going to get into bond lengths, bond distances during this lecture. However, as with everything, if you do have questions, please feel free to bring those up either in class, in conference, or come by during office hours, and I'd be happy to get into more detail with you there. So for today, or for this video lecture, we're going to primarily focus our attention on bond angles. And so I'd like to start off with just looking at a simple molecule. So we can draw a molecule like methane with a Lewis structure where you have what appears to be this flat planar molecule with all 5 atoms and all 4 bonds laying in the same plane. But this is not true, and we've, as chemists, have been able to experimentally prove that methane and really all molecules are not completely flat. They actually have a 3-dimensional structure to them. And so that we see that in reality, the structure of methane would look like this, where we can place 3 atoms all in the same plane, and then the other 2 hydrogens would either be extending out the board towards you and then one behind the board towards me. And so we would signify that by drawing a wedge to show that this hydrogen is actually sticking out of the board towards you, and then on a hash we would put the other hydrogen, which is coming behind the board towards me. And so now we have this 3-dimensional structure that's been experimentally verified for methane, right? And so this arrangement does a very, very interesting thing. What it does is it sets up the molecule so that all of the regions that have electron density in them, so all 4 of these bonds where we have electron density, are as far apart spatially from each other as possible, right? And so this is the introduction to a theory of theory of distribution of atoms in a molecule that's known as VSEPR, and you've probably heard of VSEPR before. So VSEPR, EPR, stands for valence shell electron pair repulsion, right? So we're looking at the electron pairs in the valence shell around some atom, and we know that because these electron pairs are negatively charged, and 2 negatively charged things don't want to approach each other, these similar charges want to repel each other, they're going to repel as far apart as possible. I want to modify this right now, and I want to get you to start thinking that instead of thinking valence shell electron pair repulsion, I want us to think of this more as valence shell electron domain repulsion. And we're going to see later on in this lecture why domain is really a better descriptor than pair for this phenomenon, or for this theory that we can observe. All right, so as I mentioned, the heart of this theory is the concept that electron pairs, what I like to call electron domains, as we'll see when we get to double bonds and triple bonds, repel each other. And this repulsion is whether or not that electron pair is involved in bonding. And the result is that all of these electron domains end up being spaced out as far apart from each other as possible. And that's what gives molecules this 3-dimensional nature, this ability to have things, as this example, either sticking out of the board towards you or coming behind the board towards me. Okay, so returning to methane, the result of VSEPR, this repulsion of electron domains from each other within a molecule, means that all of our bond angles are not what we see here, 90 degrees, right? But a hydrogen-carbon-hydrogen bond angle, right, when we have 4 bonds or 4 electron domains around an atom, is actually pretty close to 109 degrees. It's 109.5, but for our purposes, 109 degrees is sufficient, right? And so in the valence shell of carbon, we have these 4 electron domains. So the best way to space them out is in a tetrahedron, right? So we can imagine that the base of the tetrahedron is comprised of these 3 hydrogen atoms, right? And the top point is here, right? To make this pyramid shape with the carbon atom at the center. Now, you'll excuse my bond lengths and the imperfections in my drawing, but you know, Sorel has a good representation of this, and I advise you to check it out. I am by no means an artist. Okay, and so for this arrangement to occur, again, all of these angles between the bonds would need to be 109 degrees. So we've talked at this point, we've seen this situation where we have 4 bonds around an atom, but what would happen if we only have 3 bonds and a lone pair? So a great example of that would be ammonia. And again, what we'll see with ammonia is that one of the hydrogen atoms is in plane with the nitrogen. Our lone pair on nitrogen would compromise the 3rd electron domain in that same plane. So here's that lone pair. And then finally we would have our 2nd hydrogen atom sticking out of the board towards you, and our 3rd hydrogen atom sticking behind the board towards me. Again, this forms a tetrahedron, but there's an interesting difference in how we describe the geometry of these 2 very similar yet different molecules. Because we have an atom at every point of our tetrahedron here in methane, this is known as a tetrahedral geometry. Whereas here in ammonia, we only have 3 atoms comprising the points of the tetrahedron. That 4th or top point of the tetrahedron is a lone pair. We actually call this a pyramidal geometry. So even though they both have the same 109 degree bond angle, and we would have also here a 109 degree angle between this nitrogen-hydrogen bond and this lone pair, right? Because we're missing this atom up here at the top, we're going to call this pyramidal. When we have all 4 of these atoms, it's known as tetrahedral, right? So again, 4 electron domains. Each bond counts as an electron domain. The lone pair counts as an electron domain. These are all going to have 109 degree angles between each of the electron domains, right? Right now, each domain is a pair, but we're going to see examples where an electron domain is more than just one pair. One last example in this series is water. So water is only comprised of 3 atoms. So we have our oxygen in the center and our 2 hydrogen atoms, and I'm going to go ahead and put all 3 of those atoms in the same plane. We're going to have a 109 degree bond angle, which means we're going to need 2 more electron domains to satisfy that, and that's satisfied by the lone pairs on oxygen. So we'll see that we have 1 lone pair sticking out of the board towards you, and 1 lone pair coming behind the board 3-dimensionally towards me. And again, all of the angles between the electron domains are going to be 109 degrees. Okay? However, because we only have 3 atoms involved in this molecule, we would not call this a tetrahedral geometry. Here now we call this a bent geometry. So 4 electron domains equally spaced around a central atom. We have 3 different scenarios. When we have 4 atoms, 1 at the end of each electron domain, tetrahedral geometry. 3 atoms and 1 lone pair, this is going to be a pyramidal geometry. And finally, if we only have 2 atoms, right, and then 2 lone pairs, Still 4 electron domains, but this time we call it bent. Okay, so in our first examples where we were looking at 4 electron domains around an atom, that meant that we could only have single bonds involved, right? So how can we determine the geometry about an atom where we start to have double bonds or multiple bonds? So let's start with acetone. And we're going to look at that central carbon in acetone. If we look at these terminal carbons, right, we would see that all 4, this terminal carbon, same on each side, has 4 electron domains around it. We know that our bond angles here are going to be 109 degrees, and our geometry, because we have 4 atoms at the end of, or 1 atom at the end of each of those domains, total of 4 atoms surrounding our central carbon, right? This is going to be a tetrahedral geometry. Okay, but what's going on here at this central carbon? And this is really where the concept of valence shell electron domain comes into play. We see here, if we look at this double bond, that we don't have a pair of electrons in that region of space. We actually have 4 electrons, or 2 pairs of electrons. So we can't really, so these 2 pairs of electrons are constrained in that they have to stay in the same region of space between this carbon and oxygen atom, and so they're not going to repel each other the way the 4 domains over here do. These are involved in a double bond between 2 atoms. They have to stay together, and so a double bond is going to count as 1 domain. I'm going to move over here and let's just now look at this central atom. So we have a carbon, double bonded to an oxygen, single bonded to a carbon, single bonded to another carbon, right? And it's a neutral, so there are no lone pairs. The central carbon has a full octet, right? We still have 4 covalent bonds, but now we only have 3 regions of electron density around the atom, or 3 electron domains. Now, to space these 3 electron domains as far apart from each other as possible, what ends up happening is the bond angles become 120 degrees between each other. And all 4 of those atoms, the central carbon atom and all 3 of its substituents, can lie in a single plane. Okay? So whenever we have 3 regions of electron density around that central atom, we're going to have 120 degree bond angles, and this geometry is known as trigonal planar. Planar because all of the atoms lie in a single plane, and trigonal because if we go to the points, we can quite clearly make a triangle between those 3 outside atoms with that central carbon right in the middle of our triangle. So 3 electron domains, 120 degree bond angles. I can put all of the atoms into a single plane, and the geometry is known as trigonal planar. Okay? I want to now take a look at the oxygen atom of acetone. So if we look at this oxygen atom, it is double bonded to a carbon, and it has 2 lone pairs on it. Now, because it only has 1 other atom attached to it, we're not going to really give a descriptor for this geometry, but what I want to bring your attention to is that, again, we have 3 regions of electron density, so we have 3 electron domains, and still the distance or the angle between this lone pair domain and this double bond domain is going to be 120 degrees. And that's going to be true also for the angle between the two lone pairs. I'm pointing this out to reinforce that no matter what those electron domains are, whether they're a multiple bond or they're a lone pair of electrons, if there are 3 electron domains, you're always going to have these 120 degree angles between the domains, and all of those domains can lie in a single plane. I'm really reinforcing these bond angles and the number of electron domains and the bond angles, because this is going to play really heavily when we get to topic 7 and talk about atomic orbital theory versus hybrid orbital theory. Okay, so we've looked at examples where we have 4 electron domains, and we've looked at examples where we have 3 electron domains. Let's now look at a couple of examples where we have 2 electron domains. And I'd like to start off with acetylene. So acetylene has a carbon-carbon triple bond and 1 hydrogen on each end. And all of our atoms here have full octets. Hydrogens obviously only take 2 electrons, so we don't have any lone pairs and we don't have any charges we need to worry about, right? So what I want to point out first is that similar to a double bond, a triple bond counts as 1 electron domain, right? And again, this goes back to why I don't like the name Vesper. I'd rather have it be Vesder, but somebody else came up with the name first, and we'll learn it together. So again, this is 1 electron domain, has 6 electrons in it, but it's only 1 region of electron density between 2 atoms, right? Or between 2 locations. So again, this is one more reason why domain is a much better descriptor for this theory than electron pair, right? So if we have 1 electron domain between these 2 carbons, we have 1 electron domain between the carbon and the hydrogen. In order for those 2 different electron domains to be spaced as far apart as possible, the geometry around them, this bond angle between them, is going to be 180 degrees. And so this is known as a linear geometry. Okay? Now here we're looking at 2 bonding domains. Let's take a look at an example of a bonding domain and a non-bonding domain. And so a great example for that is going to be acetonitrile. So here we have the structure of acetonitrile, which is a common solvent in the organic laboratory. And I want to take a look at the geometry around this nitrogen atom. So we have a triple bond to this carbon, which gives us 1 electron domain. And now this nitrogen only has 6 electrons associated with it because of this triple bond. So that means it's going to need a lone pair, right? And if we kind of give a space, right, we can put our lone pair here. What we see is that we have now our second electron domain in this lone pair. So this is our second domain. And again, the angle between these 2 electron domains, one is a bonding pair and one is a lone pair, right? It's still going to be 180 degrees. Now because one of the electron domains is not involved in bonding, we don't actually give this nitrogen a geometry label the way we do for this carbon, in that it's linear. Okay, so we've now covered 4 electron domains, 3 electron domains, and 2 electron domains. These are going to be what we see most commonly in our exploration of organic chemistry this semester and next semester. But now I just want to recap here in a second and give you a breakdown of what we've seen so far. So a breakdown of what we've seen so far. I'm going to make a table like we did in a previous video lecture that covers everything we've talked about. So what are the things we need to consider? Well, we need to consider the number of electron domains. It's going to be one column for us. The types of domains, the bond angle, that they generate, and then finally we're going to do what I'm going to call the descriptor. So we started out by looking at situations that have 4 electron domains. And we saw that there are 3 basic scenarios we're going to encounter. We have the scenario where we have 4 bonding pairs. We're going to have a scenario where we have 3 bonding pairs and 1 lone pair. And then we also saw a scenario where we had 2 bonding pairs and 2 lone pairs. For 4 bonding pairs, so all of these situations, are going to have a bond angle of 109 degrees. So for the 4 bonding pair scenario, that's going to result in a tetrahedral geometry. For the 3 bonding pair scenario, that gives us a as I've said many times, don't count on me for spelling, but that will give us a pyramidal geometry. And for 2 bonding pairs and 2 lone pairs, that results in a bent geometry. Okay? We also looked at scenarios where we have 3 electron domains. We saw 2 examples of that. We saw one of those domains, 3 bonding pair domains, right? One of those was a double bond. And the other, no lone pairs. And then the other situation that we encountered was 1 bonding pair domain and 2 lone pair domain. We could also have some situations where we have 2 bonding pairs and 1 lone pair, but we didn't get into that. But again, the same behavior would be followed, and I'm going to put that because we have a slightly different descriptor for it. So we could also have 2 bonding pairs. 2 bonding pair domain and 1 lone pair domain. Again, the angle between any of the between the domains in any of the situation is going to be 120 degrees. If we have 3 bonding pair domains, that's going to be a trigonal planar, is how we would describe the geometry. If we have 1 bonding pair domain and 2 lone pair domains, we don't have a descriptor for that. And if we encounter a 2 bonding pair domain and 1 lone pair domain, that would give us a bent geometry with 120 degree angles. This bent geometry up here for our 4 electron domain scenario had 109 degrees. So we can use this descriptor in both situations. Finally, we had scenarios with 2 electron domains. And we saw 2 situations. One where we have 1 bonding pair domain and 1 lone pair domain. 1 lone pair domain, right? The angle between these 2 is 180 degrees. But this scenario has no descriptor. The other scenario we saw was 2 bonding pair domains. Again, that's going to have a 180 degree bond angle. and this is described as a linear geometry. So I hope you've noticed that as we've been moving through these, only in situations where we have at least two bonding pair domains do we have a geometry descriptor, right? So here's a good kind of table that lays all of this out. When we get to topic 7, we're going to include the hybridization of the central atom as part of this, and we'll recap this table at that time as well. So hopefully this was a nice, quick, short video. Gets into the topic of bond angles. Again, for more information on bond distances, I recommend that you go through your reading in Sorel, and the worksheet activity gets a lot of good information to you on that topic as well. As always, if you have any questions, feel free to bring them up in lecture, conference, or stop by for office hours. Thank you very much.